Thank you all for attending this final session. I believe they've left the best to last, and the room is almost full. I'm told actually more people are coming, so maybe I'll give a couple of minutes while I roll onto my agenda. So today I'll be talking about, Jenny said new standard. So this standard is only a little bit old. It was last released in 2023. So it's relatively new. It was a long period, it was in draft stage. It's an older standard. So IS25 which is a low voltage standard actually. But the concepts in this standard apply very well as far as arc flash is concerned to medium voltage as well or high voltage, because the concepts are the same. So we'll look at the standard IS4836, which is the ASNZ standard. I will look at IEEE, how it is related to AS4836. Also talk about NFPA's, the 70E, which is the Fire Protection Act from USA, because that has an impact on the standards as well. And then we'll also look at some mitigation solutions that we have implemented in studies that relate to selecting PPE, identifying the arc flash hazard risk categories. And we'll present one case study as well, which is a project we have implemented very recently. So let's move on. I think we are last, so we don't want to take all of your time. It's me and your drinks, I reckon. I'm in between. So like I said, the AS4836 is a low voltage standard on safe working on or near low voltage. And it has an appendix B, which is entirely devoted to arc flash. So the standard covers a number of topics, and arc flash is in appendix B. It's not a hard standard, like the standard doesn't say that you must, but it is a guideline and it's a recommendation, and you can use this to mitigate arc flash risk on your high voltage, even low voltage networks, because what comes out of it is very useful for you to implement. So if you don't have this standard and you are thinking about arc flash or working with arc flash at your sites, then my advice is get this standard, because this is probably the only standard you need to make things happen as far as arc flash is concerned on your facilities. You don't really need NFP 70E, because whatever is in there is embedded in this standard now. And you don't need IEEE 1584 as well, because that is more a calculation standard. It is useful for people who are calculating the arc flash hazard categories and doing all that. And we have software tools these days that are doing those calculations. You don't need to manually calculate with Excel files and all, which is what we used to do in the past. So there's good software tools like with Schneider's ETAP software, and there are other party software, third-party software that allows you to do what the IEEE recommends to do as a calculation of arc flash hazard. So my advice is, as a starting point, AS4836 for arc flash, even though it's a low voltage installation and working near low voltage standard, covers arc flash pretty well. So get that standard if you haven't got it, and guide you on arc flash. It then may refer to some of the guidelines and some of the recommendations in it. You may find that they are very onerous on you. Basically, some of the guidelines will say that you are already at Cat 4, so you need Cat 4 PPE. And you feel that that's like our very conservative guideline from the standard, and you may be better off doing a calculation based on the IEEE standard, and finding that really at your site it is not Cat 4, it is actually Cat 2 or Cat 3, which you can do by calculation. But as a starting point, it's very good. You can always refine it. So the standard has a number of definitions. It defines all the arc flash terminology that you need within the standard. A couple of them I've listed here. Everything is defined in the standard as far as arc flash is concerned. So I won't read them out, but the arc flash itself, the boundaries, PPE, the risk categories, all are defined in the standard. The main thing in the arc flash concern, I think some of you may have attended a prior session which one of my colleagues delivered, internal arcing, which was more partial discharge. So if you leave partial discharge to run its course, eventually it will lead to an arc flash of a number of years, maybe, or many years. So we don't want to do that. That's why that session was useful, because we have now technology to detect partial discharge and prevent arc flash happening. But in the worst case, when it does happen, then what really impacts arc flash is actually the incident energy. And the energy is dependent on a number of things. And one of the key factors that depends how much energy, arc flash energy is there, is actually time. Even though a lot of you engineers would know that energy is I squared T, even though we have the I that is squared, it has a significant impact, but in my opinion, the T, even though it's not squared, it's just standard T, it has a bigger impact. Because in protection world, you can make a lot of difference with time. How quickly you clear the fault has a big impact on arc flash incident energy. Quite often we find arc flash works like counterintuitive. You would think that the higher the fault current, because normally at a point in your network, you have two levels of short circuit. One is called the maximum, one is called the minimum. So you might think always that intuitively the maximum would be the worst case. But quite often we find the opposite is true. The minimum short circuit, because it leads to a longer time delay in operation of the relay, causes a bigger or a higher incident energy. So it's counterintuitive that way. So you have to do actually a calculation to get all the right answers. And quite often you'd be having a main incomer breaker tripping in, say, 400, 450 milliseconds. And with a mitigation solution, you can bring it down to, say, 60, 70. So that's a big, like 5 times a difference in time, which contributes quite a lot in mitigating the level of incident energy that you'd have at that arc flash level. So that's something to think about. It doesn't behave how you think it may behave. Linking IEEE to the Australian standards, like I said prior, the IEEE standard is more a guide to performing the actual arc flash calculation. And obviously, if you want to do precisely, you need this, follow this standard. But most of the software tools that you can buy on the market today would have this tool embedded. The tool would have this standard embedded in it. So you'd model the network and run this tool, and it'll be to this latest version of the standard. You can, however, if you don't want to do this, if you only run a low voltage network and a low level low voltage network, use the Australian AS4836 as a guide. It'd probably be good enough for you to guide you on what you need to do for arc flash. And here's an extract from the standard, which is on how to select PPE for various arc flash levels. And it is based on criteria that is defined in the standard in terms of voltage, single phase, three phase, currents, and such like. And you can see on the bottom right is where the incident energy is getting to a level where you need a higher category PPE. And the ones on the left, which are green and amber, is Cat 2, Cat 1, even Cat. So, and you can just follow the guideline and apply that to your existing network and come up with the right level of PPE for the site that you have. So that's quite useful. And what we find is that, obviously, if you got higher voltages, you got large networks like many thousands of amps, then probably the AS is a conservative. It still gives you guideline, but it's very conservative. You are like almost always having to wear Cat 4 or higher, or it's a dangerous category. You don't have any PPE that will be safe enough for your site. So then you must do a calculation to get the right numbers and then investigate how to mitigate those risks. There are a number of mitigation solutions, one of which I will describe in my case study. Obviously, once you have found the arc flash category either by guideline or by calculation, then whatever PPE is recommended, you should oblige with wearing those PPE before. One other thing, a lot of people, today modern equipment are all internal arc rated, and we actually specify criteria like it will have front, lateral, rear arc flash protection, right? So, and that holds true provided the equipment is its normal operating condition. So no covers are open, no doors are open, so even LV doors. If the equipment is as we have tested it for the arc flash or the arc internal arc rating, then you don't actually need to worry about wearing that. If you calculated Cat 4, but it's in this normal operating condition, you don't need to wear Cat 4. I mean, your Cat 1 will be fine, right? The reason being you haven't opened. Because arc flash, remember, all the IEEE and all these calculations are based on a door being open, and you are actually exposed to the conductors where the arc flash is going to happen. So if that's not the case, then those PPE are not required, because we actually guarantee our equipment to be internal arc rated, provided you do not open any cover, do not open any doors, it's in normal operating condition, then PPEs can be at a lower level. There are some other actually guidelines and standards in Australia that cover this topic, even prior to those, the AS standard that I talked about. And generally these are in mines and hazardous areas where they treat this with due respect, and you'll find these in mine safety regulations, etc., from a long time ago. So, and they are quite ahead in implementing arc flash identification as well as mitigation solutions, especially mining companies that originate from either Canada or US, because arc flash is well understood, known, and solutions being implemented for a long time. In Australia, it's more recent. We hear a lot of talk about arc flash and a lot of people working on this topic now. But in US, it's been there much, much longer. And that's why you see IEEE standards and NFPA cover this topic much, much better than any other standards in the world. And our standards are now catching up to this as well. Okay, so here's the case study. We have done a number of similar things, but this is one of the best ones we have done. And it's showcasing a arc flash study and mitigation solutions we did for a customer in Western Australia, and who were embarking on a fatality elimination program, is the program they identified this thing as. And we actually then conducted a full power system analysis and identifying the risk and mitigating the risk if there was a risk for arc flash on 17 of their low voltage switchboards. So we did a arc flash study, short circuit protection coordination arc flash study, using their tool. So of course, Schneider, we use ETAP, that's our own tool. Schneider owns ETAP since about 3 years old ago. But as a agnostic consulting organization, we sometimes use tools that the clients have. And there are a number of good tools on the market that do these kind of studies. So in this particular case, this client wanted a tool which they had a model for already, and they were already using this tool. So we were able to use that. And what we were able to do is produce an arc flash study report and a design once we found that all the sites had an arc flash issue. So there was a mitigation solution required. And then we were able to, as part of that package, design a solution from basically using one of, I think some of you may have attended a prior session which talked about our A1, A3, and the VEM321 arc flash mitigation solution relays, which are detecting the light of the arc, so the flash itself, and then high-speed tripping, the associated circuit breakers, etc. So this mitigation solution was based on that. And for this client, almost all of the switchboards were in a dangerous category. So other schemes were not, they could provide some help, like you can sometimes do protection coordination, better coordination, and are able to achieve some level of mitigation. But the level they needed, it was only possible with a high-speed arc flash relay. Occasionally, what you are able to do is, now with modern technology, in the old days when we had mechanical relays and all, you'd have always 300 millisecond grading margin between one relay and the next relay up it. These days, with digital relays, you can lower that to 200 milliseconds. And in fact, with some schemes like we call logic discrimination or zone selective interlocking, you can set multiple relays with the same time. So you can all your relays in a series, you can set them 200 milliseconds. And how they behave is they have signaling between relays, and it's very easy to do within one switchboard, like feeder to incomer, because they're within the board and there's no big distance involved. So the relay that is at the bottom blocks the relay above it, one level above, for 200 milliseconds, and allows itself to trip and not the other one, because they both have the same time as far as grading goes, so there's no discrimination. And you keep doing it as far as the relay chain goes, each blocking the upstream one. So whichever relay doesn't block, it sees the fault and it needs to trip, right? So with that scheme, you can set you can delay, speed up the grading basically and trip fast, because like I said, time is a big killer in arc flash land. So if you can trip faster, most likely you will change the category of the arc flash hazard. So in this case, we actually used a VAMP solution, which changed like 300, 400 milliseconds down to, say, 60, 70 milliseconds, which is a big impact on the time that the arc flash is there for. So we also did, and customer was a bit conservative. These days, with modern technology, we actually detect the signature of the arc. The arc has a very unique signature in terms of the light. So the relays are able to detect this. So ambient light, a flash from your cell phone, a camera, all of those kinds don't trigger that detector. So it needs to be a precise arc flash, which is it's got its own signature in terms of waveform. So there is no nuisance stripping. In the olden days, very early days, there could be nuisance stripping if someone was doing visual inspection and shown a torchlight, maybe you trip it, but not these days. But this customer was conservative, so they actually have a current check. So when the arc initiates, you also check the current in the incomer, and then if both are happening, then only you trip. So then we had to design some CTs, et cetera, for that current check scheme as well. Not absolutely necessary, like I said, but if you want to be conservative, that's one of the things you can do. Also, then new scheme, new relay. So the client needed some inspection and test planes. So you'd be developing this when you implement a scheme like this. Inspection and test records, so you can keep records of what you have tested. Quite often these are brownfield sites, so you are implementing on an existing site, so record keeping is paramount. It's not a FAT kind of situation, it's always site SAT that you're doing. We wrote a functional description on how the scheme would work, because almost always you are not able to mitigate the risk on the incoming side of your main incomer, because there's no point in tripping the incomer breaker if the fault is on the cable side or the line side of that. You need to trip upstream. So almost always you have to send our tripping signal upstream for that relay, situation. And the VAMP relay has zoning, basically. Within the VAMP relay, you can have multiple zones. So you can coach the relay to trip in a particular situation and multiple tripping signals as well. So that zone, we identify independently and trip only upstream. While if the downstream of the feeder breaker, if its fault is there, the arc flash is there, then we only trip the feeder breaker likewise. So you may have heard about the A1, A3 relays as well. So these relays are not able to do, they're more basic relays than are for smaller schemes. They're not able to do the level of zoning that the VAMP 321, that the high-end relay is able to do. So with the VAMP for this client, the largest switchboard was like a double-sided switchboard. We had close to more than 100 sensors and 4 or 5 zones, just one relay. In the entire board, we just use one relay, multiple IOs, because the IOs also can do tripping as well. So it's a more economic solution rather than having, even when we had 2 buses, you could do it with one relay, because each of the buses, you could treat them as zones. So it's a more optimized solution in that sense, while the A1, A3, the more basic relays are not able to do that level of zoning. Okay, so this is what, to implement a scheme, you should need some collateral like that. And in this case, the customer had on that drawing on the left, which we used, we built the relay onto that existing drawing, but the other drawings they did not have, so we built new drawings for the actually they didn't even have a GA, so we built a GA by visiting site and measuring the board and doing a general range, because we need to place the relay somewhere on the board and the I/O sensors somewhere on the board and the light detectors somewhere within the board. It's hard to show on a 2D drawing where the sensors would go. So it's generally, if we don't know, if it's not our board, third-party board, quite often that's the only item we leave a bit imprecise. So that's only locked in and S-built after implementation. So during commissioning, we need to send some qualified people who know where to locate sensors in Schneider boards. Of course, we know our boards, but third-party boards, quite often we have to find the best location for the sensor, which is the location that it won't be invisible to arcing, as well as cover the maximum zone and not be blocked by other hardware. So it needs a bit of skill, a skill which can be trained to other people, but quite often for the first few, we deploy our own team to make sure that is done all correctly. So here's what we sort of drawings, schematics, layout drawings, GA, test records, the study on the top right-hand side of that, you see the arc flash study extract of that. So all of this we prepare and give it as like a document package to the client to pass on to the installation and commissioning team. So this is a typical, not this particular case, but it's a general architecture, which is what we would implement for a medium voltage transformer, low voltage solution. One relay covering multiple zones. So each of those areas you see marked in green and blue are different zones and different sort of tripping schemes for arc flashes, arc faults in those areas. So you don't need multiple relays to do that. You can do it within one relay and by configuring. So this is all set up in the configuration of the relay, which actually can be done on outside prior to going to site to implement. So you do a relay config file, check it, and then send it to site for implementation. And this is a client's drawing. So this is actual 1 transformer, 2 transformer, and 2 board scenario, just still using one relay, different zoning. And this is how it was implemented. And like I say, for the incoming side of the breaker, before the breaker, trip upstream to mitigate the risk in that part. In a number of instances, we have done some boards where the client have lived with this risk because it's a low risk. It's only the incoming cable compartment and the cable side, which is under no protection if you don't trip upstream. So some people live with it. Obviously, they make sure people don't go to that part and don't open that compartment. But the other parts of the boards are then protected by the breaker, the incoming breaker that protects that network. And finally, as part of the collateral we give to the client, we give them a bill of materials for the architecture that we come up with our solution architects. Schneider have the expertise. So this essentially involves selecting the right relay, the cortex of it, number of IOs needed for the size of the board. It always varies because what we do is, and generally in low voltage, we always put a point sensor in each of the compartments. Low voltage can have many compartments. Medium voltage, only 3 compartments, the busbar compartment, the cable compartment, and the circuit breaker compartment. They're the only 3 compartments in HV switchgear. And generally, always we put a fiber loop sensor across the busbar, which is like an open tunnel all across. And occasionally we find that doesn't work in the LV because quite often, even though the LV board may say it's got a busbar compartment, they're always convoluted and they're going all over the place, so loop sensors don't work. So we found on jobs where we had sent to site loop sensors, they were never used because the clients, our installation team found that the point sensor worked better even in low voltage busbar compartments. So yeah, case by case, we have to size this bill of materials to suit the board. And that's done by basically solution architects within Schneider Electric. So that's my presentation, one typical case. And If you don't have that Australian standard, please, that's where you start. And then you can talk to us on anything more complex that the standard can't cover, which is generally modeling in your network and doing a IEEE study. I'll leave it there. Thank you so much for your time.